In this video, we'll see how to use the timer module of the MSP430 microcontroller with an HC-SR04 Ultrasonic Sensor. First, we'll look at the connections between the sensor and the Launchpad, and then we'll inspect the datasheet of the sensor in order to understand how it works. Right after that, by going through the user guide of the microcontroller, we'll understand the timer module, capture, compare, and output modes. We'll also see how to use this knowledge in order to trigger the sensor and capture the echo that it sends back to the microcontroller. Let's see the connections between the MSP430 and the ultrasonic sensor. The VCC pin of the ultrasonic sensor is connected to the 5V pin on the Launchpad. The ground is connected to the ground pin on the Launchpad. The yellow cable seen here connects the trigger pin on the sensor to the P1.6 pin on the Launchpad. And the blue cable, which is on P2.1 on Launchpad, is connected to the echo pin over the voltage divider. Here we are using 220 ohm and 470 ohm resistors to form the voltage divider. The reason for this is we'd like to reduce the 5 volts coming the echo pin from the sensor to 3.3 volt levels for the Launchpad. Now let's open the datasheet of the HC-SR04 Ultrasonic Sensor and understand how we are going to operate it with the MSP430 Launchpad. This is the datasheet of the ultrasonic sensor. Here in the electric parameters, you can see that the sensor operates between 4 meters and 2 centimeters. Below, we can see the 4 pins of the device. Now we'll take a look at the timing diagram, which is the most important for us. Here it's written that we need to supply a 10 microsecond pulse in order to trigger the sensor. So we are going to do it via the P1.6 pin on our Launchpad. And it's suggested to use over 60 millisecond measurement cycle. So this means that while this duration will be 10 microseconds, the period of this cycle is going to be at least 60 milliseconds, which means 60,000 microseconds. Then the sensor sends ultrasonic pulses, which can be seen in the second graph, which is an internal process and we will not deal with it. And as soon as the sensor receives the echoes from the objects, it sends a pulse from its echo pin, of which duration is proportional to the distance of the object. So the duration here should be received and calculated by our Launchpad's P2.0 pin. Then we are going to divide that duration, which is in microseconds, by 58 to obtain the distance in centimeters. You can see it in the datasheet as well. It's easy to say, but how are we going to do it? Let's open the user guide for the Launchpad, go to the timer section and find out. This is the MSP430 X2XX family user guide and its literature name is SLAU144J. You can find it online. In order to configure both the trigger pin P1.6 and the echo pin P2.0, we are going to use timers. Timers are one of the most commonly used and valuable modules on our microcontroller. For the trigger, we are going to use PWM, pulse width modulation, and PWM can be constructed in our device with compare mode configured timers. Now, let's go to page number 355. Here, we see the timer A module of the device. As you can read from the document, timer A is a 16-bit timer counter with multiple capture compare registers. And in the next page, you can see the main features of the timer A, of which we are going to use its PWM compare mode property for trigger, and capture mode and capture interrupts for measuring echo timestamps. Jumping to page number 357, we see one of the most important registers of the timer module, TAR register, which increments or decrements depending on the mode of operation with each rising edge of the clock signal. And it can be read or written with software. It's a 16-bit register and that's why the maximum value it can get is 65,535 in decimals. In page 358, we can see the timer modes. Among the 4 modes, we are going to be using up and continuous mode in our compare and capture blocks respectively. Let's see the operation of up mode first. The up mode is used if the timer period must be different from FFFF hexadecimal counts. The timer repeatedly counts up to the value of compare register TACCR0, which defines the period. Now let's see the continuous mode on page 359. The continuous mode is similar to the up mode. However, in this mode, the timer counts up to the fixed value FFFF hexadecimal and then restart from 0. Now let's see the capture and compare modes on page 363. We can see the definition of the compare mode. The compare mode is used to generate PWM output signals or interrupts at specific time intervals. Let's focus on the PWM output signals and quickly go to the output modes and focus on output mode 7, reset set. Let's read the definition. The output is reset when the timer counts to the TACCR X value. It is set when the timer counts to the TACCR 0 value. This is the output mode 7, and you can see that when it reaches TACCR 1, it resets, meaning that it sends 0. And when it counts up to TACCR 0, it is set, meaning that it sends high voltage. Does this look familiar? Let's jump back to the ultrasonic sensors datasheet and find out. We just saw that by using the output mode 7 and changing the TACCR 1 and the TACCR 0 values, we can generate a kind of pulse width modulation. I'll try to show this to you in the ultrasonic sensors datasheet. Now let's clear these sections so you can see that we can create this effect in the trigger input by using these timer values. Let's draw our axis first. And let's draw our triangle signal. Now you can see that this value is going to correspond to TACCR1. And the period will correspond to TACCR0. And now let's assume that we are working at 1 MHz frequency. And we have set the TACCR0 value to its maximum value, like 65,535. Since we are working at 1 MHz frequency, each clock cycle corresponds to 1 microsecond. This means that this is going to be 65,535 microseconds, or 65.5, etc. milliseconds. So this is aligned with the hardware specifications of the device, because they were suggesting that we should have a period of 60 milliseconds at least. And at the 1 MHz operating frequency, if we set TACCR1 to 10, which is hexadecimal A, we will be complying with the 10 microseconds pulse width. So by using these parameters, we will be able to send the trigger signal to the distance sensor. Now to see the capture mode, let's go to page number 362 in the user guide. Capture mode is used to record time events. It can be used for speed computations or time measurements. The CMX bits select the capture edge of the input signal as rising, falling, or both. A capture occurs on the selected edge of the input signal. If a capture occurs, the timer value is copied into the TACCR X register. The interrupt flag CCIFG is set. Now I think more or less it's understood how we are going to use the capture mode in order to keep track of the echo signal. If you take a look at the datasheet of the ultrasonic sensor once again, you remember that we were supposed to measure this time duration. And from the user guide, we just saw that by capture mode, we can record time events and we can do time measurements. So you can see that if we choose both edges for the capture signal, meaning that we are going to get an interrupt each time we receive a rising edge or falling edge of the signal, this timer value is going to be copied in the TACCR X register. So when we receive this interrupt, if we record this register's value to the first element of an array, let's for example say A0, And then whenever we receive the second interrupt and record that timer value to A1, and if we do this operation A1 minus A0, we are going to get the difference. And remember that since we were using 1 MHz as the clock frequency, this value is going to be corresponding to microseconds. Meaning that if I use this diff value and divide it by 58, I'm going to come up with the distance of the object in centimeters. Okay, I think that it's enough with the user guides and the data sheets. Now let's open Code Composer Studio and see our code. In our code, first we are going to include the libraries that we are going to use. Then we are defining some character arrays that we are going to print on the serial monitor. And in the following lines until the main function, we are also defining some additional variables that we are going to use in our calculations. In our main function, first we are stopping the watchdog timer. Then in lines 27 and 28, we are setting the clock frequency to 1 MHz. Setting the clock frequency to 1 MHz is important for us because it's going to allow us to do our calculations in a much simpler way. For example, we will be able to calculate our duty cycle for the PWM very easily. And in line 29, we are defining the P1.6 as output for the trigger pin. And in line 30, we are setting P2.1 as timer clock. And in lines 31 and 32, if we focus on bit 1 and bit 2, if for a specific pin, if we set P1 cell and P1 cell 2 bits to high, then we set them as digital communication pins. And setting bit 6 as high in P1 cell register, we are setting the P1.6 as timer and clock. Between lines 33 and 37, we are dealing with the serial communication settings. In line 38, we are selecting the SM clock and then we are selecting the up mode for the timer. In line 39, we are setting the TA0 CCR0 to its maximum value, 65,535, and this is going to be our period for our PWM. And in line 40, we are setting TA0 CCR1 to 10, which is going to be our duty cycle for the trigger. In line 41, we are choosing the output mode, and this is necessary for our PWM. In line 42, we are choosing the SM clock and we are choosing the continuous mode. In line 43, we are setting several things here. We are setting capture mode for getting the time values from the echo pin, and then we are enabling the interrupts. We are choosing the capture compare input, and here we are choosing the capture mode as rising edge and falling edge together. So this is going to allow us to capture both rising edge of the signal and the falling edge of the signal, and then we are synchronizing it. In line 44, we are enabling the general interrupts, and in our while one loop, we are printing out the measured values to the serial monitor. This may seem a bit complex, however, this is only for getting the fractional part of the data and converting it to integer again, and then sending to the serial monitor. And in line 66, we are having a 0.5 seconds of delay. Actually, maybe the most important part of the code is this section, our ISR. In our ISR, first we are getting the timestamp for the rising edge and then clearing the interrupt flag. And as the second interrupt comes, which is the falling edge, we set it to the temporary array as well. And as we get the difference in between them, this is going to allow us to measure the distance between the object and the distance sensor. Here we are going to divide it by 58 and it will give us the distance in centimeters. Now let's debug and run the code and see how the distance sensor works. Let's click on resume and let's open the terminal window. You can see that our distance sensor is aligned at around 20 centimeters and our nearest object is the wall, and it says that its distance is around 27 centimeters. So let's use another object and move it towards the distance sensor. Now we can see that the difference is around 18 centimeters. And if we come closer, we can see that the distance is decreasing, and we can see it on the monitor. Now we are at about 9.5 centimeters. If we come closer, we can see that we are at around 4 centimeters. This was the end of the video. I hope it's been useful for you. If you have any questions or comments about the code or the experiment, please write them in the comment section. Thank you for watching and see you in another video. Bye.